Welcome back, students. Today I am going to start chapter 4, Chemical Bonding and Molecular Structure. In this video, I will explain you about the meaning of chemical bonds. There are many theories put forward to explain chemical bonding, of which in this video I will focus on Kossel and Lewis approach, the theory which tries to answer why atoms combine to form chemical bonds. Dear children, you all know what matter is. What is matter? Matter is something that has mass and occupies space. Now, what is matter made up of? Matter is made up of one or different types of elements. It is either made up of the same type of elements or it is made up of different types of elements. Under normal conditions, no atom of an element is capable of existing freely in nature except noble gases. So, only atoms of noble gases have free existence. They can exist freely in nature. Atoms of all other elements are not capable of existing freely in nature. However, a group of atoms of either the same element or different elements can exist together as one species having characteristic properties. Such a group of atoms is called a molecule. Now the examples of molecule are H2O, water, nitrogen, oxygen and dihydrogen and so on. Okay, see in H2O, which is water, there are two different elements. Okay, there are atoms of two different elements. What are they? There are two atoms of hydrogen and one atom of oxygen. They exist together as one species, which is H2O. And H2O, which is water, has its own characteristic properties. Clear? Now look at nitrogen. Here you can see that two atoms of nitrogen. Okay, they are atoms of the same element. They are existing together as one species and nitrogen has its own characteristic properties. Clear? So how can we define a molecule? A group of atoms of either the same or different elements existing together as one species having characteristic properties is called a molecule. Obviously, there must be some force which holds these atoms together within the molecules. Clear? There must be some force. If you take the example of water, H2O, there must be some force which holds the two atoms of hydrogen and the single atom of oxygen together as one species. Okay, this force which holds these atoms together within the molecule is called a chemical bond. So what is a chemical bond? How is it defined? The attractive force which holds various constituents, be it atoms, ions and so on, together in different chemical species or different molecules is called a chemical bond. A number of questions may now arise in many of you. The first question that would probably pop into many of your minds would be, why atoms combine? What is the necessity? Why should atoms combine? Isn't it? Why are only certain combinations of atoms possible? For example, if we take hydrogen, we know that it exists as dihydrogen. Isn't it? In nature, we can find hydrogen existing as dihydrogen and not as trihydrogen. Why do some atoms combine while certain others do not? We know two hydrogen atoms combine to form dihydrogen. But we don't find two helium atoms combining to form He2 molecule. Isn't it? Similarly, why do molecules possess different shapes? We know carbon dioxide is linear shaped, but water is a bent or V-shaped molecule. Similarly, boron trifluoride is planar, but ammonia is pyramidal. Why so? To answer such questions, different theories and concepts have been put forward from time to time. These are Kossel-Lewis approach, valence shell electron pair repulsion theory, popularly called VSEPR theory, valence band theory or VB theory, and molecular orbital theory or MO theory. Let's learn about this one by one. Now let's look at the first theory, Kossel-Lewis approach to chemical bonding. This approach tries to answer the question why atoms combine to form chemical bonds. A number of attempts were made in order to explain the formation of chemical bonds in terms of electrons. However, the first satisfactory explanation for the cause of chemical combination between atoms was given independently by two people. Who are they? Courcelle and Lewis in the year 1916. Since their theory is based on the electronic configuration of atoms, it is also referred to as electronic theory of valency or electronic theory of chemical bonding. The explanation of Courcelle-Lewis approach regarding the chemical combination between atoms is based on the study of the peculiarity observed in the electronic configuration of noble gases. Students, imagine an atom to be like a walnut. A walnut has a shell and a kernel. The kernel is the nutty part that is edible, and it is the outermost shell that comes in contact with the world around it. So it is the outermost shell that has to bear everything, the change in weather, contact with materials around it, and so on, while the nut inside it is protected. So it is the outermost shell that might undergo any change. In the same way, Lewis pictured an atom. According to him, an atom can be viewed to comprise of a positively charged kernel that includes the nucleus along with all the inner shell electrons and an outer shell. We can relate this to a walnut, can't we? So, the well-protected nut inside the walnut can be related to the nucleus along with all the inner shells of the atom. Okay, that form the kernel. And the outermost shell of the walnut can be related to the valence shell of an atom. Remember, I told you that only the outermost shell of a walnut undergoes any change. In the same way, it is the electrons present in the valence shell of an atom that participates in chemical bonding and leads to chemical combinations. Okay, the valence shell of an atom can accommodate a maximum of 8 electrons. Lewis had a strange view. He did not imagine the atom to be like a walnut. On the contrary, he imagined it to be a cube. According to Lewis, an atom is like a cubic box, and everything inside the cubic box is the kernel, and the cube itself is the outermost shell that can accommodate a maximum of 8 electrons. Okay, the kernel inside the cube consists of the nucleus and the inner shell electrons. I hope you can understand this idea from the picture display. Students, look how the atom of sodium is represented. The atomic number of sodium is 11. It is an alkali metal in which the outermost shell is occupied by only one electron. And this one electron present in the valence shell of sodium would then occupy a corner of the cube. Okay, now what about noble gases? Noble gases have 8 electrons in their outermost shell. Then these 8 electrons would occupy each of the 8 corners of the cube. Atoms with 8 electrons in their valence shell, or in other words outermost shell, indicate a particularly stable configuration. Atoms which possess less than 8 electrons in their valence shell try to achieve this configuration by forming chemical bonds with other atoms. A chemical bond may be formed either by gaining or losing one or more electrons. For example, in the case of sodium and chlorine, a bond is formed by the transfer of an electron from sodium to chlorine, thereby forming Na plus and Cl minus ions, which are held together by electrostatic forces of attraction as sodium chloride compound, or by the sharing of one or more electrons. For example, in the case of molecules like chlorine, hydrogen, iodine, and so on, a bond is formed by the sharing of a pair of electrons between the atoms involved. So, in the process, each atom involved attains a stable outer electronic configuration of 8 electrons. Now I will explain about Lewis symbols. In the formation of a molecule, only the outer shell electrons of atoms would involve in bond formation. Outer shell electrons are also known as valence electrons. So children, let me ask you a question. If you have an atom, which of its electrons would involve in the formation of chemical bonds? What would be your answer? Only the electrons present in its outermost shell, or in other words, valence electrons would involve in the formation of chemical bonds. Now, what about the electrons present in the inner shells of atoms? The inner shell electrons are well protected and generally they do not involve in the chemical combination process. Clear? So, once again, which electrons are involved in bond formation? It is the valence electrons or outer shell electrons of atoms. Clear? Now, there's an American chemist called G.N. Lewis. He introduced the simple notations to represent valence electrons in an atom. These notations are called Lewis symbols or electron dot symbols. So, what is the other name given for Lewis symbols? It is electron dot symbols. According to Lewis notations, the valence electrons or outer shell electrons are shown by dots around the symbol of an element. These symbols ignore the inner shell electrons. Now, look at the Lewis symbols of second period elements displayed. This is how we write the Lewis symbols for various elements. Clear? What is the significance of Lewis symbols? In Lewis symbols, the number of dots around the symbol of the elements is equal to the number of valence electrons in those elements. So the number of dots around the symbol of the elements helps in calculating the common or group valency of elements. Now, what do you mean by group valency of an element? It means all the members of the group to which the element belongs would have the same valency as the element. Clear? Now, the group valency of elements is either equal to the number of dots in its Lewis symbols or it is equal to 8 minus number of dots. Okay, the following technique would help you in calculating the common or group valency of elements. Okay, the common or group valency of an element would be equal to the number of dots in its Lewis symbol when there are less than or equal to 4 dots surrounding the symbol of the element. Clear? So, if you take lithium, Lewis symbol of lithium has only one dot, which means it has only one electron in its outermost shell. Okay, since the number of dots in the Lewis symbol of lithium is less than 4, okay, what would be the common or group valency of lithium? It would be equal to the number of dot present in the Lewis symbol of lithium. How many dots are there in the Lewis symbol of lithium? It is equal to 1. Okay, so the common valency preferred by lithium would be equal to 1. Now, if you take the Lewis symbol of beryllium, there are 2 dots representing the 2 valence electrons. Okay, so you can see that the common or group valency of beryllium would be equal to 2. This is because the number of dots in the Lewis symbol of beryllium is less than 4. Clear? So since there are only 2 dots in the Lewis symbol of beryllium, the common valency that would be preferred by the element beryllium would be 2. Clear? Now, look at the Lewis symbol of boron. It has 3 dots, right? So, these represent the 3 valence electrons of boron. The common or group valency of boron would be equal to the number of dots in the Lewis symbol of boron. How many dots are there? 3 dots. Since the number of dots is less than or equal to 4, that is 3, the common valency that would be preferred by boron would be 3. So what is the valency of boron? It is 3. Let us consider Lewis symbol of carbon. It has 4 dots representing the 4 valence electrons. The common valency that would be preferred by carbon would be equal to the number of dots in the Lewis symbol of carbon, since there are 4 dots in it. Clear? So the common valency that would be preferred by carbon would be 4. Okay, So lithium, beryllium, boron and carbon have valencies, common valencies equal to 1, 2, 3 and 4 respectively. Okay, these elements would prefer to have these valencies. That is why we have mentioned common. Okay, now the common or group valency of the element would be equal to 8 minus number of dots or valence electrons in the element if these are greater than 4. Okay, if there are more than 4 dots in the Lewis symbol of an element, you calculate the common or group valency of the element by subtracting the number of dots in the Lewis symbol from 8. Clear? So these are the following examples. The Lewis symbols of nitrogen, oxygen, fluorine and neon are shown. Nitrogen has 5 dots in its Lewis symbol, oxygen has 6 dots, fluorine has 7 dots and neon has 8 dots representing their respective valence electrons. Clear? Now you can see that the number of dots in the Lewis symbol of these elements are greater than 4. So how do you calculate the common or group valency of these elements? You subtract the number of dots in these elements, okay, from 8. Now let us calculate the common or group valency of nitrogen. Okay, nitrogen has 5 dots which is greater than 4. Okay, so to calculate the common valency of nitrogen, I subtract 5 from 8. So 8 minus 5 gives you 3. So this would be the valency that would be most preferred by nitrogen. Okay, nitrogen would have a preferred valency of 3. Okay, if you take oxygen, it has 6 electrons in its outermost shell, which is represented by the 6 dots in its Lewis symbol. Okay, so the common valency that would be preferred by oxygen would be given by 8 minus 6, that is equal to 2. So this is the preferred valency by oxygen. If you take fluorine, there are 7 electrons which are represented as the 7 dots in the Lewis symbol of fluorine. So 8 minus 7 is equal to 1. This would be the preferred valency by the element fluorine. Okay, neon is a noble gas, we know that. So it has 8 dots in its Lewis symbol representing the 8 electrons in its outermost shell. So 8 minus 8, we get a valency of 0. So noble gases would prefer to have a valency 0. So this is how you calculate the preferred valencies of elements in the periodic table. Okay, so this is the significance of Lewis symbols. Now let's see what Kossel said about chemical bonding. In the periodic table, it is the noble gases that separate the highly electronegative halogens and the highly electropositive alkali metals. Since halogens are highly electronegative, they have a strong tendency to gain an electron. Thus, halogens can form negatively charged ions by gaining an electron. Since alkali metals are highly electropositive, they have a strong tendency to lose an electron. And so, alkali metals can form positively charged ions by losing an electron. The negative and positive ions thus formed attain a stable noble gas configuration, that is, 8 electrons in their outermost shell. The stable general electronic configuration of noble gases except helium is Ns2Np6. As unlike charges attract each other, the negative and positive ions are held together by strong electrostatic forces of attraction between them. For example, let us look at the formation of sodium chloride from sodium and chlorine. We know that the electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. Here, 1s2, 2s2, 2p6 corresponds to the outer electronic configuration of the nearest noble gas, neon. So, we can also write the electronic configuration of sodium as neon 3s1. Now, in order to acquire 8 electrons in its outermost shell, sodium readily loses an electron and it becomes Na plus ion. Thus, it acquires the octet configuration of neon as shown. Okay, the electronic configuration of chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. Here also, 1:2:2p6 corresponds to the configuration of the nearest noble gas neon. So we can also write the electronic configuration of chlorine as neon 3:3p5. Now you can see that there are 7 electrons in the outermost shell of chlorine. In order to acquire 8 electrons in its outermost shell, chlorine gains an electron and becomes chloride ion. Okay, thus the electronic configuration of chlorine changes from neon 3:3p5 to neon 3:3p6, which in turn is the electronic configuration of their nearest noble gas argon as shown. Now, the oppositely charged sodium plus and Cl minus ions attract each other and are held together by strong electrostatic forces of attraction between them, which constitute the ionic bond. Thus, the bond formed as a result of the electrostatic attraction between the positive and negative ions is known as the electrovalent bond or ionic bond. Cosel's views on chemical bonding were of great value in understanding and systematization of ionic compounds. However, there was a limitation to his theory. That is, a large number of compounds did not fit into the facts put forward by him. So this is about Cosel's postulates on chemical bonding. Now, students, shall we see what Cosel and Lewis concluded about chemical bonding from their independent studies? Noble gases belong to group 18. This you have learnt in chapter 3, right? They are also called inert gases. The study of noble gases suggests that they neither combine chemically with any other element nor they do so among atoms of themselves. That is, they are chemically inert. Okay, they are chemically inert elements. Look at the electronic configuration of noble gases. Can you observe something similar among all these elements? From the electronic configuration, it is clear to us that noble gases have 8 electrons in their valence shell or outermost shell. Except helium, it has only 2 electrons, isn't it? I told you earlier that atoms of noble gases in general do not have any tendency to combine with each other or with atoms of other elements. This suggests that a valence shell containing 8 electrons or octet is particularly stable. Thus, chemical inertness of noble gases may be due to the presence of 8 electrons or octet in their outermost shell. Atoms of all other elements which have less than 8 electrons in their outermost shell are thus reactive. So, children, what do you understand from what you have learned till now? Why should atoms combine? Atoms of different elements combine in order to have 8 electrons in their outermost shell or valence shell. Why should they have 8 electrons in their valence shell? What is the advantage they would get if they had 8 electrons in their valence shell? They would attain stability. They would have stable electronic configuration like noble gases. Clear? So, atoms of different elements combine with each other either by complete transference of valence electrons from one atom to another or by sharing of valence electrons in order to have an electronic configuration of 8 electrons or octet of electrons in their valence shells. Clear? Only then they would attain stability. So this is called octet rule. This is very important, children. So please learn it thoroughly and properly. Having learned the octet rule, let us now learn the modes of chemical combination between atoms. This answers the question how atoms combine. Through octet rule, we learnt that atoms combine in order to have an octet. That means 8 electrons in their outermost shell in order to attain the stable inert gas configuration. So what are the different modes of chemical combination that can occur between atoms? Let us look at the first case. by complete transference of one or more electrons from one atom to another. Okay, so chemical combination between two atoms may occur by complete transference of one or more electrons from one atom to another. The chemical bond so formed by the complete transfer of one or more electrons from one atom to another is termed as ionic bond or electrovalent bond. Okay, another different method is by sharing of electrons. This can happen in two ways. In the first case, the two combining atoms may contribute equal number of electrons to form a bond. Okay, each atom would contribute equal number of electrons to form a bond. The bond formed by equal sharing of electrons between two atoms is called covalent bond. In the second case, electrons may be contributed entirely by one of the atoms but shared by both atoms during the formation of a bond. So the bond formed when electrons are contributed entirely by one of the atoms but shared by both atoms is called a coordinate bond. This is also called a dative bond. So these are the different modes of chemical combination that can occur between atoms in order to establish chemical bonds for achieving a stable electronic configuration.